Spanning trees. What do we mean by a spanning tree? Given a graph, a simple graph, which will turn out to be connected, then we want to take a subgraph of that graph, where the subgraph contains all the vertices of the original graph, but with as less number of edges as possible. Okay, so this is what we have written here. So we start with a simple graph, and we want to get a connected subgraph with a minimum number of edges. And that connected subgraph, we want it to contain all the vertices of the original graph. So we want to get a connected graph that contains all the vertices of the original graph with minimum number of edges. And for sure we will not allow to have circuits in there. Okay, so this motivates us for the following definition. We start G assembly graph. Now we will define a spanning tree of G. So we have the original graph called G, and we want to get out of G a tree that we call a spanning tree. And why we call it spanning tree? Because it is a subgraph which is a tree that containing every vertex of G. So that's what means by span. Span means like go over everything in there. Now everything for us here means the vertices. So given a graph, we want to get out of it a tree that contains all the vertices of the graph G with minimum number of edges. Okay. And by a theorem, we will say that, okay, you might ask, can we do or find a spanning tree for every given graph G in general? Can we find a spanning tree for it? And the answer is in this theorem. It says only for connected graph. So a simple graph is connected if and only if it has spanning trees. Okay, so the graphs that we can get spanning trees for are connected graphs. And if you have a graph and then you managed to find a spanning tree for it, then that original graph actually was connected. So it is if and only if. So connected graph guarantees the existence of spanning trees, and the existence of spanning trees guarantees that the graph you started with is connected. Okay. So we will take this theorem for granted. We will not go over proof. A proof is just explaining in words. Okay. Now to make things clear, this is an example, and it says find the spanning tree for the simple graph G. This is the simple graph G in here, and we want to find a spanning tree for it. Actually, what okay. So at the left is the graph G, and at the right is the spanning tree. How could we manage to obtain a spanning tree for this graph? What we do, we will delete edges until we get as minimum number of edges, but keeping all the vertices. So the very first thing that we will do is try to get out the circuit. We will cancel circuits because this graph is not a tree because it contains simple circuits, right? The graph G. So what we want to do is to eliminate circuits. Okay, and what I will do, I will use this color, okay, to say, okay, I wanna get rid of this edge. Okay, then I look we have a circuit E, F, and G, then I will recommend that to get rid of this edge in here. And we still have one more circuit, C, F, and G. And if we delete this edge in here, oh, okay, so we get the spanning tree. Now the remaining edges, this one and this one in here, they make a tree, and together they produced a subgraph of G that contains all the vertices, right? So here we go. So this is a tree. Do you believe this is a tree? We can make it look like a tree if you wish. I can say, okay, if we take this to be F, then there is an edge goes from F to G, and another edge goes to C, and another edge goes to B, and there's an edge coming out of B and going to A, and then edge coming out of C and going to D, and there's an edge coming out of G and going to E. So it is a tree, right? We know a tree is a simple graph that has no circuits, okay, and no loops. A simple graph implies no loops, okay. Now this is what we have done. We remove the edge AE and then EF and then CG, and then we produced a spanning tree. As here means we might have more option to produce more spanning trees for the same graph. So again, below here we will have the same graph as we have done in here, but we will see other options for clearing some edges or eliminating circuits by clearing some different edges at every time, and then we produce a different spanning tree at each one of these times. Okay, now again this is the graph G again. Now to eliminate this circuit, we may remove this edge AB, and also we have another circuit in here. We remove EG, and then we have one more circuit left, CFG. We might remove this edge, and then we get a spanning tree. Okay, we can keep doing so. Now we can remove this edge from here, and if we remove this edge, okay, we get a spanning tree. If we stop here, this is not a spanning tree, because if you notice that if we stop here, then this will give us a circuit, right? So it's not spanning tree so far. So we need to remove more edges. If we remove E and G, then this gives us another spanning tree. Okay, and I will let you play with these different spanning trees associated to the same graph. So the spanning trees are not unique. Okay, now how to produce spanning trees out of a given graph. What we have seen is by deleting edges, but in here we will learn two algorithms that help us to make or obtain spanning trees for given simple connected graphs. First algorithm is called depth first search. This terminology is known in artificial intelligence, where there are algorithms to look for some vertices inside the tree, and there are many algorithms for doing so. Each algorithm has some preferences according to the applications. Okay, so let's see what depth first means. From the meaning you can guess that we keep going to the depth somewhere, and then if we don't, when we are done, then we go up, and then we go depth, kind of. Let's see. So depth first search, it says choose arbitrary vertex in the graph. So start with any vertex. Form a path starting from that vertex. How to form a path? Start as some vertex. It is incident to some edge. So choose an edge and walk with it. You will reach another vertex. Then do the same. Walk with an edge incident to this other vertex. You will reach a third vertex, and keep doing so till you reach a vertex where you cannot travel to any other vertex, or if you travel, then you will make a circuit. What you do next, let's see. In such a case, move back to the last vertex in the path, if possible. If possible, form a new path. If you cannot form a new path, move back another vertex in the path. That is 2 vertices back in the path, and try again. Okay, so let me explain what that means. We said start at an arbitrary vertex, right? So move to another vertex. Keep moving. And keep moving to other vertex. And so on. Now, at some point in here, in this vertex, we might not be able to keep moving because we might reach a leaf, or reach a vertex that has no other incident edges, or we reached a vertex so that if we move from that vertex to any other vertex, we will find ourselves moving and making a circuit. So we cannot add edges after this last vertex. And then what the algorithm says, it says go back to the last vertex. This is move back to the last vertex. So this is the last vertex. This is the last vertex. And it says go back to the next vertex, to the last vertex, which means this one here. And now try to do the same thing. Just keep following paths and vertices. Okay? But it might happen that you cannot do this. Maybe you cannot do this because there are no edges and vertices. Or if you do it, you will find yourself making a circuit. Then what you do, then go to the vertex that comes before, one more back. And that, what does it mean? Move back another vertex in the path that you made. Move back another vertex. That is 2 vertices back in the path, and try again. Now try again means try to make a path from here. Again, if you cannot, for some reasons, then go back to the vertex in the first path you made, one more vertex, and try to do the same thing, to follow the same thing till you get a spanning tree. This will be clear when we work an example. Okay, and this is called packet tracking because you have just seen we reached a vertex and then we come back to the vertex before to do the same thing, to repeat the same procedure. If we cannot, then we go back one more to do the same procedure, and that's why it is called packet tracking. Yes, I'm recording mode. I'm recording the whole lecture today. Okay, so use first depth search to find a spanning tree for the given graph. Okay, now it says start at any vertex. Now the book here you chose to start at F. Okay, and then what does it do? Then it says okay, I will move to another vertex, to G, then I will move to H, then I move to K, then I would choose move to J. Okay, so it made that path. Now at J we cannot move anywhere, so the algorithm says, okay, go back vertex. So you are at K. Can you move and make a new path? No. Okay. So go back one more vertex, and then we are at H. Can we move somewhere? The answer is yes. We can move to I. So at H, we added an edge that is going to I. Good. Now at I, we cannot move anywhere. Then the algorithm will tell you to come back at H, and then it asks you again, can you move anywhere now? Well, somebody may say, oh, okay, we can move to F, but this movement is not allowed, because if you take this edge, then you will make a circuit, right? And we are supposed to get a tree. Tree contains no circuits. So coming back at H from I, we'll find ourselves we cannot move. Then we go back more and more on the original path. G, we cannot go anywhere. Okay, go to F. Okay, once we go to F, then we find that we can move to D. Okay, good. So from F, we moved to D. And then from D, we moved to E. Good. And then I cannot move from E to F because then I will make a circuit. Okay. So I will choose to move the other way to C. Then we added C. And then we go to A or to B. Doesn't matter. Go to A. And then we add A in here. Now, once we reached A, we cannot go anywhere. So the algorithm tells you come back to the next vertex, to the last vertex you were in, which is C. And then once I comes back to C, I can go to B. So there are branches at C in here. So we added B. So we had from F to D to E to C to A, but C will goes to B and D. And now putting these things together, we have produced a spanning tree. So this is a spanning tree. Okay, so this is the way to produce a spanning tree. Now notice here we started at F, while we could start at any other vertex, and I will leave it for you to go and start at E, for instance, and see the spanning tree you will get. Okay, and we can maybe make it for quick. So I want to start at E, and to do so I need to erase all of that. I would like to play with it a little. So okay, I will choose to start at E. Come on. Okay, at E. So here we go. Then I go to C. Okay, so I will say, okay, I added C. I go to A. Then I added A. Then come back to C and then go to B. Then I get B in here. And now I will keep going back as the algorithm says. Now I came back to E, then I can go to D. So from E to D, and from D to F, and from F to G, from G to H, and I can guess now H I can go to K, and also I can go and K takes me to G, and also K takes me to G, and H takes me to I. So this is another spanning tree of this graph using the same algorithm, depth first. Okay. Now why they call it depth first? If you noticed, once we formed this tree in here, we used we went the deep way till we are done. So we went the deep way till we are done, we reached the bottom, and then the bottom again, and then deeply to A, and then the bottom again. Same thing in here. So it goes deeply. This is why it is called depth first. We give a priority for going deep. Now another algorithm will give a priority for going in the depth, in the breadth, in the levels. We'll take a level, and then at a level it will not go down in the priority, but it will go at levels. It will give the priority of levels and then going down the levels. So we will call it breadth first algorithm. And what does this algorithm says? Breadth first algorithm: choose an arbitrary root, vertex as a root of the tree, then add all edges incident to this vertex. So you choose a vertex, but this vertex is connected in the graph to other vertex, so make them in level 1. So this is level 1. And now this is a vertex in the graph, and it is connected to other vertices, and maybe this connected to one vertex and this connected to 2 vertices, and be sure not to make a circuit, and this will be called level 2. And then we keep going till we obtain all the vertices. Okay, now we will execute this algorithm, perform this algorithm on this graph. So at the beginning we started at E, and now notice that E is connected to B and to I and to F and to D. So here we go, to B, to D, to F, to I. So the ones that are connected to E, the root which have chosen, the vertex we have chosen as a root, are put in the first level. Now if we go to F and see, it is connected to G and J, right? So here we go, F is connected to G and J. Good. Now if we go to I, it is connected to H. It's okay, we can do it. Let's follow what the book is doing here. Okay, notice we cannot go from I to G, because if we do so, then we form a circuit, and this is not allowed because that will not be a tree anymore. So we will go from, we could go from I to K and to H, but the book here chose to go to K only. Okay, and from D we go to H, from D we go to H. Okay, so I will show you, I said the book chose that way, so we'll go just to explain what we see in here. We can make a different spanning tree using this algorithm, as we have done in the first depth. Okay, let's keep going then to B. B goes to C and to A. Here we go. B goes to C and A. And now what's left? Let's see. We got this vertex, this one, this one, this one, and this one, this one, this one, and this in here, and this in here. So what this one is left, and it comes out of K. Here we go. And also L is left, and we can reach it from G. Okay, and we are done with the spanning tree. A spanning tree. Okay. Now again, we can play with it with this graph, and using the breadth first algorithm to produce a different spanning tree. I said a little while ago that the book chose it that way, so we will go with the way of the book, but let us work it the way we want. Why don't we start at F? So I will take F. Now F is connected to G and to C, E, and G. Okay, so I will go here. F is connected. I will put G in here, and I will put C in here, and E in here, and G. Okay, now let's go to G. G is connected to L, so we'll take it connected to L, and we will not take this because we will make a circuit. Okay, now let's go to C. C goes to B. C goes to B. Here we go. Okay, and we can say, okay, B goes to A also, and we can say B. Okay, so let's leave it there. I can reach D from A or from E, so let me choose to reach D from E. So I will take this to be D, and reach I from E, so this will be I, and then I will say, okay, let's choose, let us reach H from I, so this is H, and reach K from I, here we go, and reach M from K, here we go. Okay, this is another spanning tree using breadth first. Okay. Minimum spanning tree. So as we have seen before, given a certain graph G, then we can produce more than one spanning tree. Now, if the graph is weighted, which means the edges have values, then the spanning trees, the different spanning trees consisting of different edges, will have different weights for this, different summation of weights, because the spanning trees are different because they are different in choosing the edges, but each edge has a certain weight, so we can take the sum of the weights of the edges of each one of the spanning trees. The spanning tree that gives us the minimum weight, we will call it a minimum spanning tree. So let's go for it. It is defined in here. A minimum spanning tree in a connected weighted graph is a spanning tree that has the smallest possible sum of weights of its degrees, that have the smallest possible sum, and the smallest here goes among all the spanning trees that can be obtained for a given graph. So how we figure out or obtain the minimum spanning trees? We do so by following one of the two algorithms. The first algorithm is called Prism Algorithm. What does it do? Begin by choosing any edge with the smallest weight. Successively add to the tree edges of minimum weights that are incident to a vertex already in the tree. You are constructing a tree. So let me explain what that says. You have a graph. Go choose any edge with the smallest weight. Okay. So in the graph in there we have 1. And then once you choose that edge, then it has 2 vertices at the end, right? Okay. So choose one of them. Choose one of these vertices. Now look at the edges incident to this vertex. okay, and take the smallest, the edges with the smallest weight. Once you do so, then you added another edge, okay, so one more vertex has joined the tree. And then from that vertex and also from the vertices you have already, look for the smallest, the edge of the smallest weight, and then choose it. Okay, so I will be able to make it clear through working this example. Okay, now, okay, it says choose an arbitrary edge. Okay, I want to follow the choices of the book. Okay, so at the beginning it chose from B to F. You see, it will choose. Okay, so now we will be forced to go the same as, because of this choice, we'll be forced to go the same as what the book has in here. Okay, let's see. So we chose this edge. Now, what edges you can see from any of these two vertices? Like if you are at B, then you can see a vertex, an edge of weight 3 and of weight 2, right? And if you are at F, you can see an edge of weight 3 and weight 4. Good. Now take the edge that has the smallest value. Now remember, you can see what B and F can see. Okay. Now this come out to be the smallest edge, so we will take it. And then vertex A is added. Now your eyes are on the vertices B, A, and F, and you look at all edges that you can see from every one of these vertices. Okay, and choose the smallest weight. I forgot about this 2 in here. Okay, now I can see from F, I can see this edge and it has 2. Why I choose it? Because 2, this 2 is smaller than any number that I can see from A. I can see 3. From B, I can see 3. From F, I can see 3. And from F this way, I can see 3. But from F this way, I can see 2. So this is the smallest. So I have eyes on A, B, and F. And I found that this is the smallest, and then I will take it. So G has joined the tree. And now I will have eye on G. That means I am standing on G and looking at the edges, and I will see there is a 3, an edge which is incident to G, which has weight 3, and this has weight 3. Now I have eye on B. I can see 3. I can see 3 from F, and I see 4. And from A, I see 3. And from G, I see 3, and I see 3. Okay, so the minimum number, the minimum weight is the 3, and it is repeated 5 times. I can choose any of them. And we will go with the choice of the book. It chose this one here. Okay? Now, the vertex E has joined the tree, and from E I can see 4. Okay? I will not go that far because I can see an edge with a 3 from the vertex B and the vertex F and the vertex G. So I will choose to go from G to I. I wanted to choose this edge. And actually we are going, I'm explaining to you why the book is choosing them this way. You could choose going from G to K, or F to G, or B to C. You could choose any one of these. Okay. Now I has joined the tree, and I can see from I an edge going to 4, so I have this value added. Okay, now from B I can see an edge with the 3. Same thing from F and from G, so we will choose this one. You can choose any one of them, so we are choosing this. Now G has joined the 3, and from G I can see an edge with weight 2 and with weight 4 and with weight 3. So choose the smallest. The smallest one comes out to be from G to C. Choose the smallest whenever there is such a one. Okay, so now C has joined the 3. I can see from the vertex C an edge of weight 1. I will not choose this anymore. This edge will not be chosen anymore, because if I choose it, I will make a circuit and then I have no tree anymore. Okay? And now I can see 3 from the vertex G, 4 from the vertex G, and 3 from the vertex J, but I can see 1 from the vertex C, and it is smaller than any other value, other weight, so I will choose this edge. Now from D I can see 5, okay, and from G I can see 3, 4, 3, so choose any one you want. So we can go okay, so let's see, we have chosen C and D, C and G, okay, C and D, and then G and H. Okay, so we either choose this edge from G and H or from J and K. Both of them has edge 3. Now I can see from H here a weight of 3, okay, and a weight of 5. Now I will not choose this anymore because it will make a circuit. So we see weight of 3, weight 4, and weight 3, and then we will choose one of them. So we will choose that, and then we have L, and from L we can see an edge whose weight is 1, and it is the smallest among the ones we can see, which is 4 and 3. So we will choose the edge with weight 1, and then we are done. If we choose more edges, then we will make circuits. Okay, so this is the way it goes. We started with F. From F we chose B. From B we chose A, and from A we got E, and from F we got J. From J we went to I. From F we went to G. From G we went to C, and C to D. Again from G to H, H to L, and L to K. So this is the spanning tree with minimum weights, and you can fill the weights. In here it is 1, for instance. From C to D is 1. From H to L is 3. From G to H is 3. From G to C is 2. F to G is 3, and so on. Okay, so this is Prim's algorithm. We could have more choices. Like at some stages we had 3 edges or 5 edges. Each of them has the minimum weight of a 3, and we could choose any one of them. And if we do so, we will always reach to a spanning tree whose summation of weights will give 24. And this is the summation of weights we get. So I encourage you to work this again, but make different choices of edges than the ones in here. Okay. Now another method or another algorithm for obtaining a minimum spanning tree, which is cross-call algorithm, and it says it will choose edges. Okay, this way, let's see. Choose an edge in the graph with a minimum weight, and then successively add edges with minimum weight that do not form simple circuits. Oh, okay. What that means? In Prism algorithm, we chose an edge with minimal weight, and then we stand the vertices and look at edges that has minimum weight, and then we keep adding edges and standing and vertices and look at edges again. But here what we do, we will go and say we will choose a minimum edge. Okay, so we choose this one here. Okay, so we are done. So we chose an edge that has minimum weight. Now it has weight 1. So are there edges that has weights 1? If not, then I will go to edges that has weight 2. If not, then weight 3, and so on. But wait a minute, we have edges of weight 1. So we will take this. Okay, we have more edges of weight 1. Good. Okay, so we will take this. So no more edges of weight 1. Then I will go look for edges of weight 2. Do we have some? Oh, okay. So we will have this edge of weight 2. And more edges of weight 2. Yes, this is an edge of weight 2. We will take it. And this is another edge of weight 2. We will take it. Any more edges of weight 2? No. Now we look if there are edges of weight 3, then we take them. If there are not, then we look for edges of weight 4. If they are not, then we go look for edges of weight 5, and so on. But we have edges of weight 3, and we can take, okay, we'll take that. Okay. Now we will also take, we can play with it. We will take this. And now we will take any one of these. We will take that. Okay, we have too many 3s in there. Edges with weight 3. Okay. And notice once I took the last one, I will not be able to take this anymore because if I take it, I make a circuit. And I will not take this anymore because otherwise I will make a circuit. Can I take this one? Yes. And this is 3. Can I take this one? Yes. Okay. No more edges of weight 3. Now we go and see edges of weight 4. Now this is an edge of weight 4, but I cannot take it because there will be a circuit. And I cannot take this one because there will be a circuit, right? A circuit, which circuit I mean in here? If I take this, then I get this big circuit, right? Okay. Now I cannot take this one because it will make a circuit. So I can't take no edge of weight 4. Let's go to weight 5. This is the only edge of weight 5. Can I take it? I cannot because that will make a circuit. So we are done. No more edges left. So we can draw a tree. Then we started with F, and then B. From B we choose A, and from A we chose E. From F we went to J, from J to I, and from F we went to G, and from G we went to C and H. From H we went, there is H, to L. So these are the vertices. And from L to K, and from C to D. So we got this tree and add the weights of the for them. This is 1 and this is 3, this is 3, this is 3, this was 1 and 2, 3, from F to G was 2, F to B 1, 2 and 3. Now if you add the edges, then we get 24. Now let's go back and see what we got here. In both algorithms, in both examples, we used Kruskal algorithm a second time. First time we used Prim's algorithms, and if you notice, they produced the same tree. So this tree that comes from Prim's algorithm for this graph G is the same as this tree, and we still have the same graph G, and this the same tree and the same edges, the same summation of weights of the edges. Okay, and this brings us to the end of this lecture.